Welcome, everyone. This is the afternoon session. We have a very exciting line of works to be presented this afternoon. The first talk is going to be given by Elena Grigorescu on local codes for insertions and deletion.
Okay, thank you. So first, thanks to the organizers for inviting me, and thanks to all of you for coming back from lunch. I'll talk about local codes for insertion and deletions, and this is it's based on 3 papers with these co-authors, Alex Block, who just graduated from Purdue, Jeremiah Blocky, who's my colleague at Purdue, Quan Cheng, who's my colleague at Peking University, Shubham Kulkarni, who was an undergrad at the time of this research, Xin Li from Johns Hopkins University, Yu Zheng, who just graduated from Johns Hopkins, and Minchen Zhu, who is my student, and he's there. So address the hard questions you have to him. I also copied some of his slides. So I will try to go very quickly over these definitions. Most of you have seen them, but let's just quickly review them. So we're going to talk about insertion deletion codes. So edit distance between 2 strings X and Y over the same alphabet is the minimum number of symbols you need to delete or insert into X to obtain Y. So for example, for X equals 0, 1, 0, 1 and Y equals 1, 1, 1, the edit distance is 4 because you need to delete the zeros and insert instead ones. You probably are more familiar with this notion of Hamming distance, which is the number of indices where X and Y differ. And there is this inequality relation between edit and Hamming distance. You can think of it as if edit distance is large, then Hamming distance is large. So now some jargon about codes. We encode messages of length n over alphabet sigma into code words C of x of length m. And we would like to have this associated function d, which given as input C of x outputs back x. And we actually want more from this function. We wanted to output back x even when there is some error into the encoding. So some parameters that we care about when we talk about codes are the minimum distance, which is the minimum distance between, a relative minimum distance between 2 code words. And we can think about Hamming and edit distance, and this should be something in 0, 1. And the rate, which is the ratio between n and m. And when we want to construct codes, we want to add as little redundancy as possible. So m versus n, m should be kind of very small compared to n. So the rate should be theta of 1, and distance should be also theta of 1. We want to be able to correct from as much error as possible. So we want the code words to be kind of far away from each other. So when we have such a property, we call these things good codes. And in terms of algorithmic goals, we want efficient encoding and decoding. So we want this function d to be efficient, mainly. So in terms of INSDAL codes, they were introduced by Levenstein in the 60s. And only maybe 40 years later, 30 years later, we have efficient constructions of good codes with efficient decoding. And only recently, this area of building codes that are as good as possible in terms of both encoding, decoding, like asymptotically good, and in terms of algorithmic linear encoding and decoding and variants like list decoding, we have recently kind of a lot of works, and probably I'm missing a lot as well. Here are some great surveys if you want to read more about it. So in this talk, I'm going to look at variants of these codes called locally decodable codes. So these are codes where not only we have efficient, but we actually care about something else. We care about super efficient decoding. So we don't want to output the whole code word. We want to output 1 bit of the code word. but much faster than it would take us to decode the whole code word. So for every message bit I, we want to be able to query the received word, which is the code word plus some error, and the output xi with good probability. So this is the kind of formal definition, but all you need to know is that you can make at most Q queries. That's called the locality of the code, and you would like to be able to withstand some delta fraction of errors. So this is the prototypical example of a locally decodable code, right? The Hadamard code, what does it do? It encodes n bits into 2 to the n bits. It looks like this at position. So you can think of the code word as being indexed by vectors in f2 to the n. And at position A, we just take ax mod 2. Okay, that's the Hadamard code. And I drew it here. Now, what is a simple local decoder for this code? So suppose you have a delta fraction of error. Here is a 2-query decoder. Pick A uniformly at random. So pick a position in here uniformly at random. Flip the ith bit of A, which is, it's the same as writing query at A plus EI, and output this value. So y at position A plus y at position A plus EI. So if there is no error, this is exactly xi, you can convince yourself. If there is error, it's xi with probability, you can check half plus epsilon. There is a union bound in there involved. Okay, so this is a 2-query locally decodable code for Hamming errors. So we know quite a lot about Hamming errors. Now, what about insertion deletion errors? Can we build locally decodable codes when instead of Hamming, we have a delta fraction of insertions and deletions? Okay, that's kind of like, it's still an open question even after our work. So so I didn't say anything about motivation, but as motivation for locally decodable codes, there has always been this motivation that you want to decode a file from a library in time that is proportional to the file size rather than to the library. And it turns out that in this recent paper, people in DNA storage technologies care exactly about this, and they are, in terms of biotechnology, they are at the point where they're looking at random access into these encodings. And why is this kind of relevant to our work? Because DNA storage is mostly affected by insertion and deletion errors. So they're kind of looking at locally decodable codes. Okay, so what do we know about insertion deletion codes? So there is a paper from 2015 by Ostrovsky and Parskin-Chernyavsky, which shows the following. Well, first of all, where would you even start? Okay, perhaps the kind of natural way to start is, well, let's take a Hamming LDC. Can we make it robust to INSDAL errors? And that's exactly what these people do. So suppose you have a Q-query Hamming LDC, correcting a delta fraction of Hamming errors, then you can transform it into an INSDAL LDC, a binary INSDAL LDC, where the query complexity blows up by polylog the size of the code word. Okay, so there is a blow up in the query complexity. However, the rate and fraction of error that it can correct is actually just a constant, blows up by just a constant factor. Okay, so this is, so we were writing this paper 5 years later, and at the time when we were going to submit it to FSCTCS, we actually found that the wheel has been invented before. But anyways, we kind of reproved this result using different techniques, and also we had some new questions that kind of motivated further work. And in terms of locally decodable codes, there are only maybe a handful of other papers that look at slight variants like channels that are memory bounded or randomized encoding and decoding. And yeah, so that's pretty much it. And this is a subset of the co-authors of this work. Yeah.
Same as the n above, or this n is also n log sigma? Maybe you can repeat the question.
Yeah, it's and okay, sure.
Should preserve the rate, is it?
I mean, within a constant factor, the rate is preserved. Okay, so you're saying forget about log sigma. Yeah, okay, yeah, sure. Thanks. Okay, so rate and distance just blow up by a constant factor, but we get a polylog here. So what, in terms of like transforming the LDCs that we know of at this point into, I mean, the Hamming LDCs into Insdal LDCs, we get the following kind of bounds. So for Q equals 2 queries, we know the Hadamard code. It has exponential length. We get codes of poly and query complexity and again, exponential length. Is that interesting? It's very non-interesting. Q equals 3 constant. So this is a very exciting line of work by Ekanin and others when they discovered that there exists sub-exponential length 3-query LDCs. That again doesn't imply anything too interesting in this setting as well. So where things start to be interesting is in the polylog query regime. So here we have, it's the setting of read-Muller codes. We have locally decodable codes with polylog and queries and almost linear length. And we get pretty much the same bounds for Insdal. And similarly, in the polynomial query and slightly subpolynomial query regime, we have constant rate codes and we get exactly the same things here. So I'll talk a little bit about the reduction itself to kind of get more intuition about what these codes look like or what the reduction looks like. So what they do is take the message encoded using the outer Hamming LDC. So what does that mean? You can actually recover every bit of the message using Q queries into this code. But we want to make it a bit more robust against Insdal errors. So we break it into a bunch of blocks, each block of length log m. Then we attach the index to the block. And this is something that one typically does when they're working with Insdal codes, because that's kind of the issue with Insdal codes. You don't know where indices might have shifted. So you kind of attach it to the information symbols. And then we apply the Schulman-Zuckerman code that we've seen before, which is a constant rate, constant distance, efficient decoder code. And to make it even more robust, we add a bunch of buffers, of 0 buffers. Also, the length of these things is about the same log m. Okay, so that's kind of even the SZ code is built kind of in the same way. So this is like a standard way to build Insdal codes, but we want to make it locally decodable. So if there is no error, how do you decode? How do you decode at position I? So what you would do is kind of simulate the outer decoder, figure out where each query went. And we know precisely, if there is no error, we know precisely where each query went. We decode the SZ codes and that just output the output of the decoder on those queries. Now, the problem when we have errors is that, again, things might have shifted, things might have been deleted, some blocks might have intersected each other now. one hard thing to do here is to kind of search for index I locally. Right, so how do we do that when we have errors in the encoding? And kind of tied into that is finding the location of the buffers and the buffers. So some properties that are helpful of the SD code here these are kind of, it's useful to us to have a polytime decoder algorithm because it's going to take only polylog m time to decode a block. And that's in kind of our query regime. And one interesting property here is that actually, if we look at the code word, SD code word, there are many ones in the encoding. So 2/5 of some segment of every segment of length theta k is actually pretty dense in ones. So that's kind of nice because that helps us distinguish zero blocks from information blocks. Okay, so so back to the question, how do we find a block J when the code is corrupted? Well, first thing you would think about is binary search, but now there are errors, so we want to do some sort of noisy binary search. And one observation here is that there can't be too many corrupted blocks because we have a bounded amount of incident error that we're allowed to use. So there aren't going to be too many corrupted blocks, which will allow us to kind of guide the binary search. So as a toy problem, which is pretty much kind of the high-level idea of the decoder, suppose you have an array, it's delta sorted, which means that if you delete a delta fraction of the elements, then you get a sorted array. Find an element of the array. Right, so this is a very standard question. Ronit talked about something similar a few days ago. And there are many variants in the literature of noisy binary search. Here, what we do is, because most indices are essentially in order, we can perform a binary search around the median. So it's kind of like a recursive search. And kind of the main idea is that we need to make sure that the amount of error does not, the density of errors does not increase on the side that we're going to recurse on. And sometimes it can increase, and there are indices that we will never be able to recover. But many indices are something called locally good, which means that every interval that contains them has small error density. And one can show that all those indices can be found. And there is a constant fraction of them, and we can essentially do this noisy binary search in polylog n time. Something like log to the 4th. So as a quick summary, we have a transformation from Hamming to INSDAL LDCs with polylog m loss in query complexity, and just a constant fraction of loss in rate and decoding radius. We have absolutely no implications in the constant query regime. And this, what we've seen, the noisy binary search kind of begs two questions, namely, is noisy binary search kind of inherent to local decoding? Right, you need to find, it looks like, I mean, it feels like you need to find indices. Like, can you find indices if you are just allowed two queries without doing a binary search? So if not, do there exist constant query LDCs? So let's talk about constant queries, constant query LDCs. So this is the second paper that that I'll talk about. So we've already seen these three columns of the table. In terms of lower bounds, what's known is for two queries, there is an exponential lower bound. So Hadamard is tight for two query Hamming codes. And for more than three queries, the lower bounds are pretty weak. Right? So there is a huge gap between the upper bounds that are slightly sub-exponential and the lower bounds that are almost linear. So this is like the biggest question in terms of locally decodable Hamming codes. So what about INSDEL codes? So what we can show is, so first of all, Hamming errors are edit errors. So the lower bound for Hamming LDCs, two query Hamming LDCs does hold. So we have an exponential lower bound holding there. We can show that there are no linear two query INSDEL LDCs. So as far as I know, pretty much all constructions of constant query LDCs are actually linear codes, but there are no such things, no two query linear codes in the INSDEL model. And then we have some exponential lower bounds for a Q greater than or equal to 3. So before for Hamming, the bounds are kind of almost linear. Here we have really exponential lower bounds. So pretty strong lower bounds in the higher than Q equals 3 regime. And this kind of like goes smoothly up to something like log n over log n, where they look something like this. And then around log to the 5th n, kind of everything breaks, the lower bounds and the upper bounds. So we don't know what's happening over there. So I want to say a few words about the proof of the lower bound. And before that, I want to say a few words about how people prove lower bounds for constant query LDCs in the Hamming model. So the idea over there is that you can focus on local decoders that are smooth, which means that they only they query each bit of the encoding kind of uniformly. So there isn't any index that is queried too much. And then one looks at the Q queries as an edge in a hypergraph with m vertices. And one can show that there exists a large matching in this hypergraph, so something like of size omega m over q. And then there are very complicated proofs to kind of analyze this large matching via various techniques. Okay, so the way we think about our lower bounds is, so we're looking at this set for each index I, each message bit I. We're looking at the tuples in the code word side of things, such that if we project the code word onto those Q tuples, there exists a function that kind of predicts the ith bit with good probability. Okay, so this is kind of the equivalent of the matching thing, yeah, of the hypergraph edge. So Kat and Trevisan, ever since they introduced this model, they show that Q is good for just a couple of indices, cannot be good for many indices. And one can show that this set, for every I, this set is actually hit with good probability. So we want to decode with good probability. So we want to be able to find these queries, hit these queries with good probability. So that's another property of this set. And now the question that we're asking is kind of what deletion patterns make a decoder work hard. Okay, so this is a kind of where we diverge from the Hamming view of things. So this is kind of the conceptual contribution here. We're asking how can we, what deletion process can we come up with such that no matter what decoder we would have, would make it work hard to be able to predict each bit. Okay. Okay, so let's talk a little bit about what deletion patterns we could even start considering. So consider a code word here, and suppose we have some deletions. Forget about insertion. So we just have some deletions now, and index k prime ends up here, and let's say index L, which I'm writing as k prime plus d prime, ends up here. Right, so they kind of shift a bit to the left, both of them. So notice that I'm writing k and k plus d and k prime plus d prime, rather than just kl and k prime l prime, let's say. And that's because it turns out that for Inzdal codes, the distance between queries actually plays an important role. And this is something that we don't actually see in the finite fields codes. There is no kind of notion of distance. So in what follows, we're kind of, we're going to try to understand how does D and D prime behave with respect to each other. So let's think about one simple deletion pattern. So suppose you have your code word, and all we do is we pick a random length prefix and we just drop all those bits. Okay, so this is my deletion pattern. I'm just dropping many symbols at the beginning of the code word. So if I want to make this query k and k plus d in y tilde, where could it have come from? Okay, and because I'm kind of really shifting everything by e, it comes from tuples of this form, right? So what property do these tuples have? The distance between the first and second query is exactly the same, which is d. Okay, so that's one observation. I think that's a good place to make this definition. We're going to be interested in what's called the induced distribution. So for each query KD, we're going to be interested in the distribution that it could have come from upstairs. So under the error distribution, what is the distribution up here? Okay. So one question we might ask is, for this simple deletion pattern, what kind of, can we build some locally decodable codes? And it turns out that Hadamard actually gives us a solution here, because if you recall the previous local decoder, one can restate it as follows. So instead of picking A and A plus CI, we're going to pick a random pair that is a distance to the I, assuming that I'm listing things in lexicographic order. Okay, so it turns out that actually just a little bit of massaging of the Hadamard code actually gives us 2 query LDCs for these patterns with exponential code word length. So another type of pattern one might think about, deletion pattern, would be just pick a deletion probability P and drop each entry of the code word with probability P. So one can observe that D prime is concentrated around D over 1 minus P. So in expectation, we have P P errors within any interval. And one can show that any distance d prime close to this expectation appears with probability something like 1/square root of d. Okay, and that's good. It's in the right direction, but it turns out that we need something even more. So in particular, we'd like to have this property happening with probability 1/d. So for that, we tweak a little bit this distribution. And what we do is we pick P, the deletion probability uniformly in this interval, and delete each bit again with this probability. And then we combine deletion type 1, so the prefix deletion, and then this deletion type 3. And it turns out that this distribution is good for us to get a lower bound for 2-query Innsdale codes. There is a question.
Yeah, so I was wondering if you combine the type 1 and type 3, is that exactly the same distribution with you delete each bit with probability with 1/d or something like that?
Probably not. I don't know, Minchan, do you know? I don't think so.
Okay, yeah.
But yeah, thanks. Okay, so this is just for the sake of intuition, right? This is the kind of deletions we're interested in. Under this deletion pattern, we get the following property of the kind of induced distribution, namely that for every KD query, if we look upstairs at K prime D prime at the induced distribution in the before errors, we can show that D prime is with high probability within a factor of 20 from D. And moreover, every length in this interval, D20D, is kind of hit with probability 1/d. So there is no length that gives us length D more often than something like 1/d. So it turns out that if we recall the heating lemma, we have that the decoder must hit the set good I with this probability, which implies that there exists some good query that looks like KD, for which the induced probability, the probability of the induced distribution hitting good I is also large. And now we ask the question, what does the induced distribution for KD looks like? And what we will show, and maybe I might not spend too much time on this because I want to get to the last part of the talk. But what we can show is that if we kind of map K, this is M here, on this axis and the D on this axis, then there is this region, a stripe of height about order of D, such that many of a constant fraction of these pairs, KD, belong to the support of the induced distribution. So by the smoothness property and concentration property, we can show that the support actually has a constant fraction of such pairs. So this is kind of like the smoothness property that we encounter in the LDC version of things. So in particular, from here, the proof is not much longer than what we have here on the slide. This is for the sake of intuition. So we consider kind of intervals of lengths, of geometric lengths, say 20 to the j minus 1, 20 to the j. And there is one such interval where we have this nice property happening, which we can write as the fact that good I intersects this region with constant probability. And from here on, one only needs to kind of upper bound a quantity like this, double summation from below and from above. From below, because for every I there exists such region R, we get an omega n lower bound here. And from above, because each good query is good only for a few, many I's, we get an upper bound that is log t. So from here, we get that m is exponential in n. So we proved an exponential lower bound for two query Innsdale LDCs, which I already told you that is not interesting because we already had it. But it's interesting because of, well, it generalizes. So these ideas actually generalize to proving non-existence of affine and linear two query Innsdale LDCs. And also it generalizes for 3, 4 constantly many queries. It's also kind of interesting because this is just kind of combinatorial arguments for proving this exponential lower bound, for which we had kind of non-quantum arguments, but they still had a quantum flavor. So somehow, I mean, in some sense, it's still interesting because it gets rid of the quantumness of the previous lower bound for two queries. And in order to generalize this argument to more queries, one can come up with a couple of properties. I'm not going to go through that. I know it's a lot of symbols, but a couple of properties that are similar to what we've seen so far. And so, for instance, the general smoothness property says that here we have k minus 1 distances between q minus 1 distances between the q queries. We hit every distance with kind of this probability. And kind of an immediate technical conjecture is, can we improve this bound here? Can we build distributions with better upper bounds? Okay, now I'll spend the next few minutes talking about the third paper I wanted to talk about, and that's about a relaxed version of locally decodable codes. They're called the relaxed LDCs. They were introduced by Madhu and others. And here, the only difference from before is that the decoder is allowed to say, I don't know. Okay, it's allowed to output a bot, but it shouldn't output the incorrect answer with probability more than half minus epsilon. And we have actually 3 properties here. The first one is perfect completeness, which means that if there is no error, we do want to always output xi. And this is a more technical property. I'm not going to get into it. But the interesting thing about these codes is that all of a sudden, one can get constant query relaxed LDCs of almost linear length, which is extremely surprising. Okay, another kind of a smaller result here is that actually the third condition doesn't even matter because it's implied by the first 2 conditions. And we call an RLDC with the first 2 properties weak RLDC and one with satisfying the third one, strong RLDC, because actually for Innsdale, they will all matter. Okay. And there are also matching lower bounds, and these are kind of recent works. So a question that was raised by Gur and Lacic in 2021 was, okay, we know that there exists a constant query for which the code word length drops so much, but what about at q equals 2? And they conjecture that there is actually an exponential lower bound. So in these new results that are under submission, we do prove this result. So for relaxed locally decodable codes in the Hamming setting, there is an exponential lower bound for 2 queries RLDCs, which kind of implies an interesting phenomenon. So basically, we have exponential lower bounds at 2 queries, and there exists a Q for which we have almost linear upper bounds. So somewhere in the middle, there is a query complexity where the code word length drops from super polynomial to polynomial. So from Q to Q plus 1, it drops from super poly to polynomial in N. So one immediate question would be, where exactly does this happen? So what does it even happen at Q equals 3, 4, 5? We have kind of no idea where this drop could happen. So another question we ask is, what about INSDEL relaxed locally decodable codes? Here we have kind of 2 main results. One is that if we just take into account the first 2 properties, we can actually build INSDEL RLDCs with the same parameters like for Hamming. However, if we are going to enforce that all 3 properties hold, we must have exponential lower bounds for every constant. So therefore, weak and strong is not, RLDCs are not the same objects in this setting. So let me finish up with the open questions. So most of them we have seen. I guess it's interesting to figure out where this threshold happened for kind of like the phase transition, both for Hamming and weak INSDEL RLDCs. One property that we use kind of heavily in the lower bound proof is the perfect completeness property. So we want to be able to decode always correctly if we don't have error. And the lower bounds for larger Q actually hold without perfect completeness, so the ones from the literature, Lachish and Gur. So one open question would be, can one get, again, exponential lower bounds if we don't enforce perfect completeness? Then this question that we've seen is noisy binary search inherent to constructions? And if not, which this I think is the most interesting question, do constant query LDCs exist? So even like below log square, so maybe one can improve a little bit the binary search, but even at below of log square n, we don't know if we can actually get anything. Finally, there are many applications of Hamming RLDC. So like in private information retrieval schemes, PCPs, self-correction, and so on. Can one come up with significant or interesting applications of INSDEL LDCs? So that's all I want to say. Thank you.
Thank you very much. Any question for Elena?
I have a question related to this noisy binary search. So could you remind me this delta n fraction, is it randomly placed or is it adversarially placed?
Adversarial.
But then how can you get polylog n? Imagine you have your target planted inside a block of delta n non-sorted values. Then how do you manage not to look for all of them?
No, so you are never going to be able to recover all of them. So there is only a constant fraction of indices that you will, that's what we can ensure.
Okay.
Yeah,
okay.
So definitely you cannot find all of them.
Okay.
So only those locally good J's are findable.
So I'm very curious, are there even like codes in this final open question that you have? Are there order of one query locally decodable codes, install codes? Can you even get those with an arbitrarily large constant number of code words?
We don't have any construction.
Right.
Like,
so it seems like, I mean,
any
maybe
rate,
like over the
any-
binary alphabet with insert deletion of 1/3, maybe you cannot have any code with even 10 code words. Right. And query complexity of 3.
like with small. Yeah. Okay.
So
we
it's
we
like
haven't thought
explicit
about
constants may be ruled
specific
out.
small things, but yeah, that's a good question actually.
All right. Any other question? Or if not, let's thank Elena again.